There's a particular kind of stillness that arrives very late at night. Not chance, not exactly, but something underneath billiance. The fan somewhere in the house cycling on. The faint creak of a wall adjusting to the cold. That specific weight of a room when nothing in it is asking anything of you. That's roughly the feeling I want to start with. Not because it's a metaphor for anything, just because it's the right register, the right speed for what we're going to sit inside tonight. A star is not quiet. That's the first thing to get out of the way. At its core, and we're talking about the actual geometric center of a thing that contains, in the case of our Sun, roughly 333,000 times the mass of Earth, the temperature runs somewhere around 15 million degrees Celsius. The pressure is so extreme that it doesn't map onto any physical intuition a human body carries. We don't have a sensation for it. You can say the number, you can write it down, but you cannot feel it forward into your body the way you can feel, say, the pressure of lying under a heavy blanket. It's just a number sitting there, waiting. And yet, from the outside, from here, from this distance, a star in the middle of its life looks almost serene. It hangs. It burns slowly. It does not visibly change across a human lifetime, or 10 human lifetimes, or 1,000. The sun that was in the sky when the first writing systems were being scratched into clay tablets in Mesopotamia is, functionally, the same sun that came through your window this morning. Not meaningfully older, not noticeably different. Whatever is happening inside it is happening too deep and too gradually for the surface to report back in any timescale we can register. That is the stillness I mean, not silence, contained violence. Two forces, and really it is two forces, no more complicated than that, though the details of each are staggering, are pushing against each other with an intensity that would be, if you could stand at the boundary between them, the most extreme experience physically possible. On one side, gravity pulling everything inward. Every atom in the star pulling toward every other atom, the whole enormous mass of the thing wanting, in the most stubborn and impersonal way imaginable, to collapse. Gravity isn't subtle about this. It isn't patient in the way we use that word. It's just constant. Always. Doesn't rest between attempts. On the other side, the energy released by nuclear fusion. Heat and pressure and light pushing outward from the core. A continuous outward force generated by the fact that at the center of the star, hydrogen nuclei are being fused into helium, and that process releases energy, not a little energy. The sun converts something like 600 million tons of hydrogen into helium every single second, and the energy that comes from that, the energy that comes from the mass difference between the hydrogen going in and the helium coming out, which is small but not nothing, that energy is what holds the star up. It is essentially a controlled explosion lasting billions of years. And the thing about a controlled explosion, the thing that makes it feel like stillness from a distance, is that when the control is working, there's nothing to see. You only notice the explosion when the control fails, which eventually it codes, which is not tonight's story. Tonight's story is the stillness before that, the part that lasts. I used to think stability was simple, or at least I used to treat it as the unremarkable part, the boring part between the interesting events. And then I spent a long time reading about stellar physics, and I kept running into this fact. The sun has been maintaining this exact balance for approximately 4.6 billion years. It was doing this before the Earth existed, before any planet in this solar system existed. Whatever it was orbiting, whatever thin cloud of gas and dust was slowly condensing into something recognizable, the sun was already doing this, burning hydro, pushing back against gravity, holding itself open. That's not boring. I'm not sure what it is, but it isn't boring. The technical term for this state is hydrostatic equilibrium, which is a phrase that sounds like it belongs in a textbook, and it does, and there's no reason to be precious about that. But stripped of the textbook context, what it describes is just balance. A very specific, very violent, very ancient kind of balance. The kind where both sides are constantly exerting enormous force, and the net result is stillness. Think about the last time you held something heavy in an outstretched arm. The stillness in that gesture is deceptive. Your muscles are working hard. Every fibre involved in the hold is active, not resting. The stillness is not an absence of force. It's an equilibrium of forces so precisely matched that no movement results. A star is that, scaled up by a factor that doesn't have an intuitive ceiling. What's interesting, and I keep coming back to this, is that the equilibrium is self-regulating. It has a kind of feedback built into it that seems almost designed, though it isn't designed at all. If the core of a star gets slightly too hot, the increased pressure pushes the outer layers outward slightly, which lowers the density slightly, which cools the fusion rate slightly, which reduces the outward pressure, which lets gravity pull things inward slightly again. The star breathes, not literally, but thermally, structurally. It responds to perturbations and damps them. It corrects. This has been going on for 4.6 billion years. There's a detail I find genuinely strange, and I want to just leave it here without building too much around it. The light we see when we look at the sun is not newly made. The photons that left the sun's surface this morning, the ones that actually hit the earth, that came through your window, that maybe made a square of light on the floor, those photons were generated at the sun's core something like 100,000 years ago, maybe longer, depending on how you model the process. A photon of light born inside the sun takes that long to work its way outwards through the dense, opaque plasma of the solar interior, scattering and reabsorbing and bouncing, a random walk from the center toward the surface. And then, once it finally escapes into open space, it crosses the distance to Earth in 8 minutes. 100,000 years to get to the surface. 8 minutes to get to you. I don't know what to do with that exactly. It just sits in my mind as a kind of object. Heavy and a bit awkward. The sunlight on the floor this morning was old in a way that the floor isn't. That's either interesting or it isn't, and I find that it is, though I can't entirely explain why. The weight of a star in the literal physical sense is something the human body has no organ for. There is no sense that reports it. You can learn the number. The sun's mass is approximately 2 times 10 to the 30th power kilograms, but you cannot feel the number. What you can feel, maybe, is this. The Earth is held in its orbit by the sun's gravity. The entire Earth, with everything on it. Every mountain, every ocean, every city and ship and sleeping person. All of it held in a slow, curved path, around something 150 million kilometers away. And that something is just sitting there, burning steadily, not moving, maintaining a balance it has maintained since before anything here existed. Stars like our sun spend roughly 10 billion years in this phase. The main sequence, it's called, the long, stable, productive middle of a star's life. Our sun is about halfway through that, which means it has been doing this for as long as it will continue to do it. And none of that is visible. None of that registers on a human day. The star rises, crosses the sky, sets. You go inside, the fusion continues. The balance holds. There are stars much heavier than this one. Stars where the same balance holds, but the stakes are different. The fuel burns faster. the equilibrium is maintained more violently and for a much shorter time. And when those stars move through their fuel, the story that follows is not the one the Sun is heading toward. That story starts with what comes after hydrogen. This sleepy physicist is entirely self-funded. There's no production company, no backing. Just this, made carefully, one topic at a time. If it helps you sleep or think or just feel a little less alone in the dark, you're welcome to support the work over on Patreon. The link is in the description. It keeps this going. Hydrogen lasts a long time. That sounds like an obvious thing to say. Of course, the first fuel lasts the longest, there's more of it. But I think the sheer duration is worth actually sitting with before anything else. The Sun has been burning hydrogen in its core for 4.6 billion years. It will burn hydrogen for another 5 billion approximately before that particular process winds down. So when we talk about a star's life, we're talking about something where the first chapter alone runs for 10 billion years. That's not a long time in the way that Tuesday is a long time. That's a different category of duration entirely. I was trying to think of an analogy for it last week. Sitting at my desk with the kind of mild headache you get when you've been reading the same papers for 3 hours, and I couldn't find one. Every human comparison either undershoots by so much that it's useless, or it collapses under its own weight the moment you push on it. 1 billion years ago, the most complex life on Earth was still largely microbial. That's 1 billion. The Sun's main hydrogen phase is 10 of those. It's just a long burn. A very, very long and largely uneventful burn. During this time, the star's core is doing one thing. Hydrogen nuclei, protons essentially, are being fused together through a sequence of reactions, the dominant pathway being something called the proton-proton chain. 4 hydrogen nuclei go in, 1 helium nucleus comes out, some energy is released. The helium, being heavier, sinks gradually towards the centre. Hydrogen from the surrounding layers replenishes the supply. The core slowly, imperceptibly accumulates helium. Nothing about this looks dramatic from outside, nothing about this looks like the beginning of anything. But there's a detail that doesn't get mentioned enough, I think. The helium building up in the core isn't burning. Not yet. It's just sitting there, inert, taking up space. And as more and more of the core converts from hydrogen to helium, the hydrogen-burning region has to move outward, into a shell around the growing helium center, chasing the remaining fuel. The star adjusts. The equilibrium holds, but it holds differently now. Slightly reorganized, the architecture shifting the way a building shifts when you move load-bearing walls without the whole thing coming down. This goes on for billions of years. And then the hydrogen in the core is genuinely exhausted, not depleted, not running low, but finished. And the core, no longer generating outward pressure through fusion, starts to contract under gravity, slowly. The contraction heats the core, the temperature climbs, and at some point, somewhere around 100 million degrees Celsius, the helium that has been sitting there inert for billions of years suddenly reaches the threshold for fusion. Helium burning begins. I want to be accurate here. Helium fusion is harder to start than hydrogen fusion. The threshold temperature is roughly 6 times higher. This is because fusing helium, specifically fusing 3 helium nuclei into 1 carbon nucleus through something called the triple alpha process, is genuinely finicky. It requires not just high temperature, but a very specific alignment of nuclear resonance energies. A coincidence that Fred Hoyle famously predicted must exist before it was confirmed experimentally. Because if it didn't, there would be no carbon in the universe, and here we are. It works, but the process is almost fussy about it. Like it agreed to work and then kept adding conditions. Helium burns faster than hydrogen, not a little faster. Significantly faster. A star like our Sun, if it were going to complete a full helium-burning phase, would burn through its helium in something closer to 1 billion years rather than 10. The fuel is less abundant and the reaction less efficient. The clock is running differently now. What accumulates this time is carbon and oxygen, heavier still, sinking to the centre. For a star the mass of the Sun, this is roughly where the story of internal burning ends. The core never gets hot enough to ignite carbon. The star will expand, shed its outer layers, and then leave behind the carbon-oxygen remnant, the white dwarf, without ever proceeding further down the chain. But for a star significantly more massive than the Sun, the story doesn't stop here. The carbon core contracts, the temperature climbs again, carbon ignites. Carbon burning produces neon, magnesium, sodium. It lasts. In a massive star, maybe a few hundred to 1,000 years. The same pattern as before. Fuel accumulates, phase ends. Core contracts, temperature spikes, next threshold crossed. But the intervals are shrinking. Each successive phase burns hotter and faster than the last, because each fuel is harder to ignite and the energy yield per reaction is lower. The star is running the same play with diminishing returns on a shrinking timeline. Neon burning, roughly a year. Oxygen burning, months. There's something almost distressing about that compression, if you allow yourself to feel it. 10 billion years of hydrogen, then 1 billion years of helium, then a few hundred years of carbon, and now months. The thing that took 10 billion years to build is now spending its inheritance in months. I don't assign meaning to this. Stars don't have stakes in their own longevity, but the numbers do something to me when I put them in sequence like that. There's a quality to the acceleration that feels, I don't know, irreversible in a way that the earlier phases don't. Silicon burning comes last. And silicon burning is strange. The silicon doesn't fuse the way earlier fuels did. At the temperatures required, something like 3 billion degrees, the gamma rays in the core are energetic enough to start photodisintegrating nuclei, physically breaking them apart, and the particles released, protons, neutrons, helium nuclei, get recaptured by other nuclei rearranging themselves in a cascade of reactions that progressively builds toward the most stable configuration nuclear matter can occupy. The whole thing is less a fire and more a rearrangement. A settling. What it settles into is iron. Silicon burning lasts approximately 1 day. 1 day, in a star that has been alive for millions of years, some massive stars live for only a few million, burning through their fuel violently fast compared to something like the Sun. The final active phase of nuclear burning lasts about a day, maybe 2, and at the end of that day the core is iron. Or more precisely, a mixture of iron and nickel near iron's mass number, the nuclear species that sit at the absolute bottom of the binding energy curve. The bottom. Iron is where the energy gradient stops. Every element lighter than iron releases energy when fused into something heavier. Every element heavier than iron requires energy to be created. Iron sits exactly at the trough, so the most stable nucleus. The one that represents the endpoint of a process that has been building heavier and heavier elements across the entire lifespan of the star. There is nowhere left to go from iron that releases anything. The chain that started with hydrogen, that ran for millions or billions of years through every available fuel, ends here. The core fills with iron, quietly, without announcement. An iron core growing at the centre of a star that, from the outside, still looks like a star, still shining, still enormous, still hot. The outer layers have no idea. The light coming from the surface is still coming from fusion happening in shells above the core. The star looks fine, but the iron core has stopped generating outward pressure. And gravity. Gravity is still there. What happens next happens fast. Faster than fast. The timescale we've been working in are billions of years, millions of years, months, days, is about to change one more time into a unit that doesn't accommodate any of the previous ones. The next chapter takes place in under a second. Iron doesn't burn, that's the whole problem really. That's if you were going to reduce an entire stellar catastrophe to a single physical fact, that would be it. Iron doesn't burn, it sits, it accumulates. It waits with the kind of patience that isn't patience at all, because patience implies something held back, and iron isn't holding anything back. It's just done. It arrived at the most stable configuration matter can occupy, and it stopped there. The way water stops when it finds the lowest point in a landscape and has no more gradient left to follow. The iron core grows. Not quickly by human standards, but in the lifetime of the star this is fast. Silicon burning, the process that produces the iron, lasts roughly a day. Maybe 2, the core is accumulating iron peak elements at a rate the star has no mechanism to counteract, no fusion process left to ignite, no next fuel waiting in reserve. Everything that came before, hydrogen, helium, carbon, neon, oxygen, silicon, every phase had a next phase. Something to contract into, something to heat up towards, some threshold that once crossed bought more time. Iron has just no next phase. I'm sitting here at almost midnight. The radiator in this room makes a faint ticking sound when the heat comes on, a dry, irregular, metallic tick that I've stopped noticing most nights. But tonight I can hear it, and I keep turning this fact over. The core of a massive star spends millions of years building toward iron. The whole nested sequence of burning, the entire architecture of shells, hydrogen shell, helium shell, carbon shell, each layer fusing above a heavier core, the entire thing has been a long, stage process of arriving here, at this element, at this endpoint. And the endpoint just sits there. Iron nuclei, the most tightly bound nuclei in existence, which sounds like a strength. And it is, in one sense, it takes enormous energy to break them apart, and fusing them together doesn't release energy. It requires it. The binding is so complete that there's nothing thermodynamics can extract from it. The star spent billions of years climbing a ladder of progressively heavier elements, each rung releasing energy that bought time, and iron is the ground. There are no more rungs. The ladder ends here and there's nowhere left to step. The core at this point is roughly the size of Earth, roughly 1.4 times the mass of the Sun. Some models put the critical mass slightly differently, but this is approximately where the threshold sits, packed into a sphere maybe the diameter of Earth, supported still by electron degeneracy pressure, which is a quantum effect. Electrons, being fermions, resist occupying the same quantum state. And this resistance generates a kind of pressure even in the absence of thermal energy. It is the last thing holding the core up. It is not going to be enough. Here's the hesitation I have about saying what comes next too cleanly. The timeline is so compressed that ordinary language starts to lose grip. We spent billions of years in hydrogen, months in oxygen, a day in silicon. What comes after iron is measured in milliseconds. The same sequence that took 10 billion years to run is about to produce its final event in less time than it takes a raindrop to hit the ground. The iron core, sitting inert, growing, no longer generating outward pressure, reaches a mass where electron degeneracy can no longer hold. This is the Chandrasekhar limit. About 1.4 solar masses. When the core exceeds this, it falls. Not slowly, not gradually. The outer core collapses inward at roughly a quarter of the speed of light. The inner core, the very centre, compresses from something Earth-sized to something maybe 20 kilometers across in a fraction of a second. The temperature spikes to 100 billion degrees. Electrons are forced into protons. Protons become neutrons. Neutrinos are produced in a number so large the word enormous doesn't approach it. More energy in that neutrino burst than the sun will emit across its entire 10 billion year life. And they flood outward through the collapsing stellar material like it isn't there. The core has become briefly a proto-neutron star. Whether it stays that way depends on mass, whether the neutron degeneracy pressure that halts the collapse is sufficient, whether the bounce and shockwave that propagates outward has enough energy to escape, whether what's left behind is a neutron star or something that doesn't stop collapsing. That question is not iron's problem. Iron did its part. It accumulated. It set. It brought the star to the edge of the only thing gravity had been waiting to do since the moment the star was born. The chapter that follows this one doesn't belong to iron, or to gravity, or even to the star in any meaningful sense anymore. It belongs to the shockwave, to what moves outward, to what gets made in the violence and then scattered across parsecs, across millions of years, into the gas clouds that will eventually condense into other stars, other planets, into, among other things, you. I want to tell you what a millisecond feels like before we go inside this. You blink, a full deliberate blink in roughly 150 milliseconds. A hummingbird's wing completes one stroke in about the same. The gap between the moment you decide to catch something falling off a table and the moment your hand actually moves is somewhere around 200 milliseconds, maybe more. These are the things that feel instantaneous to us, the things we classify as too fast to be experienced as duration. The collapse of a stellar iron core, from the moment gravity wins to the moment the inner core reaches nuclear density, takes about half a second. I'm sitting here with a cup of tea that has gone cold as they do, and I keep pressing my thumb against the ceramic of the mug just because it still holds a little warmth. And I'm thinking about how to give you a half second that has any weight at all. Because half a second, said plainly, sounds like nothing. It sounds like the pause before someone answers a question. It is not nothing. Let's stay in the physics. The iron core, roughly 1.4 solar masses, Earth-sized or close to it, is no longer generating outward pressure through fusion. We established that. What holds it up in those final moments is electron degeneracy pressure, the quantum mechanical resistance of electrons to being compressed into identical states. This is not a weak force. In white dwarfs, electron degeneracy holds stellar remnants stable for billions of years. It is genuinely sufficient, up to a point. The point is 1.4 solar masses, give or take depending on composition and rotation. When the iron core crosses that threshold, when it accumulates just enough mass that the degeneracy pressure can no longer balance the weight above it, the collapse is not gradual. There is no slow compression, no warning phase, no intermediate stage where things are merely difficult. The core goes from supported to unsupported essentially instantaneously, and then it falls. The outer core, everything above the inner few tenths of a solar mass, begins falling inward at speeds approaching 70,000 kilometers per second. That's roughly 23% of the speed of light. This is freefall. Genuine gravitational freefall in an object that a moment ago was a stable stellar core. The material doesn't heat gradually, it hits the inner core. At around 10 milliseconds after the collapse begins, the inner core reaches nuclear density. Nuclear density is the density of atomic nuclei. the density at which protons and neutrons are packed together inside an atom. This is, in a meaningful sense, the maximum density that matter composed of baryons, protons and neutrons can reach before the strong nuclear force pushes back. There is no denser stable state for ordinary matter. The inner core has compressed to this density, this hard physical ceiling, and when it hits that ceiling it does something that ordinary collapsing material doesn't do. It bounces, not gently. The inner core overshoots its equilibrium, compresses slightly past nuclear density, and the strong nuclear force, the thing holding atomic nuclei together, the most powerful force in nature at short range, pushes back. The core rebounds outward. This generates a shockwave, a genuine outward propagating pressure wave moving through the infalling outer core at supersonic speeds, carrying the energy of, and this is where language becomes genuinely insufficient, the energy of roughly 10 to the power of 44 joules. I'll try to give that number some traction. The Sun, across its entire 10 billion year lifespan, will emit approximately 10 to the power of 44 joules of energy as light and heat. The shockwave from the core bounce carries that much energy and releases it in seconds. Not billions of years. Seconds. The Sun's entire lifetime output concentrated into the first few seconds of a stellar collapse. Most of that energy, and this is the part I find genuinely strange, the part that took me a while to fully absorb, most of it doesn't come out as light. It comes out as neutrinos. Neutrinos are produced during the collapse, when the density becomes so extreme that electrons are forced into protons, a process called electron capture, or inverse beta decay. Protons absorb electrons and become neutrons, and in doing so they emit neutrinos. At nuclear density, this process happens at a rate that produces something like 10 to the power of 57 neutrinos in the first 10 seconds of the collapse, a number with 57 zeros, flooding outward through the collapsing stellar material, and then outward through the star's outer layers, at nearly the speed of light. Neutrinos almost never interact with matter. A neutrino can pass through a light year of solid lead with only a 50-50 chance of hitting anything. They pass through the Earth constantly. Hundreds of billions of solar neutrinos pass through your thumbnail every second right now without stopping. In normal conditions, neutrinos are effectively untouchable. Inside a collapsing stellar core, the density is so extreme that even neutrinos are briefly trapped. They take milliseconds to diffuse outward through the inner core. When they escape, they carry roughly 99% of the total energy released in the collapse. The light of the supernova, the thing that makes it visible across galaxies, the thing humans have recorded for centuries when nearby stars explode, that's the remaining 1%. The brilliant visible explosion is the afterthought. Here's where I want to be a little careful about what I'm saying, because I want to get this right. The shockwave from the bounce is energetic enough, in principle, to blow the star apart. In practice, as it moves outward through the infalling outer core, it loses energy. It stalls somewhere around 100 to 200 kilometers from the center, because it's pushing against material that is still falling inward, and because the nuclei it passes through are getting photodisintegrated, broken apart by the high-energy radiation, which absorbs energy from the shock rather than transmitting it. The shockwave nearly dies, whether it dies or revives, whether the neutrinos depositing a fraction of their energy into the stalled shock are sufficient to reinvigorate it, whether the turbulence and convection behind the shock help it push through. That is one of the genuinely unsolved problems in stellar astrophysics. Supercomputer simulations in 3 dimensions are only now, in the last decade or so, starting to produce models that actually explode. The mechanism is real. The details are still being worked out. What's left at the centre when the shockwave finally propagates outward depends on their mass. For cores that end up below roughly 3 to 5 solar masses after the collapse, a neutron star. Neutron degeneracy holds. The object stabilizes at maybe 20 kilometers in diameter, spinning fast, immensely dense, city-sized, and mountain-massed. For cores above that threshold, nothing stops the collapse. Nothing. The neutron degeneracy pressure, the last physical resistance the universe can offer against gravity, fails. The core keeps contracting. And at that point, the physics we have good descriptions of stops being sufficient. And what forms is a region of space-time where the escape velocity exceeds the speed of light, and that's where this chapter ends. Not because the physics stops, because the next part is a different kind of thing entirely, and it needs its own space. The collapse took less than a second. The star that contained it had been alive for millions of years. These two facts belong to each other, and I'm not sure they resolve into anything comfortable, and maybe that's fine. The shockwave leaves the core and enters the star. This takes, or depending on the size of the star, depending on how extended the outer layers are, somewhere between hours and days. The core collapse itself was milliseconds. The bounce, the neutrino burst, the re-energization of the stalled shock, seconds to minutes. But the star is enormous. The shockwave has to travel outward through hundreds of thousands of kilometers of stellar material before it sees open space, and it moves through that material not like a wave through still water, but like a pressure front through something that is simultaneously falling inward and being heated and photodisintegrated from behind. It pushes, it stalls and gets pushed again. It carries in that propagation an energy budget that doesn't really have a human equivalent. And it carries something else. Actually, let me back up slightly, because I think the standard way of explaining this obscures something important. The common version goes, heavy elements are made in supernovae. Which is true, but incomplete in a way that matters, and I want to be precise here. The elements produced through hydrostatic burning, the carbon, oxygen, silicon, sulfur, calcium, iron, those are made during the star's life, in the core and shells, across millions of years of steady fusion. The supernova itself doesn't make those. What the supernova makes, what the shockwave produces in its passage through the outer layers, is something different. The shockwave compresses and heats the material it moves through. This drives explosive nucleosynthesis, fusion reactions that happen on timescales of seconds rather than millions of years, producing elements that the slower burning processes can't easily reach. Nickel-56, which decays to cobalt-56, which decays to iron-56. This radioactive decay chain is actually what powers the visible light of a supernova for weeks after the initial explosion. The decay energy feeding the brightness we see from Earth. But beyond that, there's a process that happens in certain regions of the explosion, in the neutrino-driven wind coming off the nascent neutron star, and possibly in other sites depending on the model, called the R process. The R process. Rapid neutron capture. This is the one I find genuinely strange. Not strange in the way that all extreme astrophysics is strange, but strange in a more specific, more personal way that I'll get to. What it describes is a process where atomic nuclei are bombarded by such an intense flux of free neutrons. Actually, intense is the wrong word. It doesn't cover it. It's more like a physical saturation of neutron density, a crowding of matter at the nuclear scale. That the nuclei absorb neutrons faster than they can undergo radioactive decay. They grow, they accumulate neutrons faster than beta decay can shed them, building up along the neutron-rich side of the nuclear chart into territory that doesn't exist under ordinary conditions. And when the neutron flux eventually drops and the unstable nuclei do decay, they cascade down into stable configurations that correspond to elements we know, specific, identifiable, measurable elements. Gold is an R-process element. So is platinum, silver in significant part, lead, uranium. So is europium, which sounds obscure but shows up in spectroscopic observations of old stars as a tracer of R-process enrichment, and astronomers use it almost like a fingerprint. So is iodine, which is worth noting for reasons I'll come back to. These elements, heavy, neutron-rich, sitting in the upper half of the periodic table, they don't form in stellar cores through normal fusion. Iron is the endpoint of normal fusion. Everything heavier than iron requires a different mechanism, a more violent context, a neutron flux that doesn't exist in a stable star. For a long time, core collapse supernovae were considered the primary site of R-process nucleosynthesis, and they may still contribute. The debate is genuinely ongoing. But in 2017, the LIGO and Virgo detectors caught gravitational waves from two merging neutron stars, an event called GW170817, and the follow-up observations in light confirmed something remarkable. The merger produced a killer nova, a specific kind of explosion that glows in infrared because it's thick with newly synthesized heavy elements. Strontium was identified in the spectrum. The signatures of R-process elements were unambiguous, so neutron star mergers are definitely an R-process site. Whether supernovae are also a major site or a minor one, or whether the contribution varies with the stellar environment, that's still being worked out. The answer probably isn't clean. The universe doesn't tend toward clean answers for things like this. What's clear is that the elements heavier than iron in your immediate environment, in the room you're in the ground outside, in your own body, were made in violent neutron-saturated events. Either the collapse and explosion of massive stars, or the collision of neutron stars, or both, made in seconds or milliseconds, then scattered. The scattering is its own thing to sit with. When a supernova explodes, the outer layers of the star, everything above the surviving remnant, are ejected into the surrounding space at speeds of thousands of kilometers per second. This ejector, enriched with the products of both the pre-supernova burning and the explosive nucleosynthesis of the shock, expands outward into the interstellar medium. It mixes with existing gas. It becomes part of the diffuse material between stars. It travels slowly over millions of years, dispersing through the galaxy in a kind of gradual contamination or contribution, depending on how you feel about the word contamination. Eventually somewhere, a region of this enriched gas cloud becomes dense enough, through some perturbation, some gravitational instability, to begin collapsing into a new star, and the planets that form from the leftover material around that star are made of whatever the cloud contained, including the R-process elements, including, if the geometry and timing were right, material that was inside a different star entirely, billions of years earlier. The iodine in your thyroid gland, and I'm not using this as a metaphor, I mean the actual iodine 127 in your actual thyroid, the element your body uses to synthesize hormones you cannot survive without, is in all probability R-process iodine. Made in a stellar explosion or a neutron star merger, scattered across space, incorporated into the molecular cloud that became this solar system, locked into the rock that became Earth, concentrated over geological time in the ocean and soil, absorbed into the food chain, into you. I was reading about this on a cold afternoon. I remember it specifically because the heating in the building I was in wasn't working properly, and I'd been sitting with my hands tucked under my thighs for warmth, which is not a dignified posture for encountering cosmological facts, but is the one I was in, and I kept pressing on the specific case of iodine because it felt different from gold or platinum. Gold you can hold, look at, keep at a distance. It's beautiful and external. But iodine is running your metabolism right now. There is R-process material made in a nuclear explosion that happened before the sun existed, operating inside your body at this moment, doing biological work without which you would die. That's not a metaphor. That's just where the iodine came from. I don't know how to feel about it, fully. There's something that wants to be profound about it, and I'm slightly suspicious of that wanting. The universe didn't make R-process elements so that your thyroid would work. There's no teleology here, but the fact of it, the plain documented isotope traceable fact that some of what you're made of was forged in a nuclear explosion and scattered across a galaxy and found its way here. That fact sits in me with a weight I can't entirely account for. The shockwave moving outward through the star in those first hours, carrying its cargo of new elements into the surrounding space, had no destination. Nothing was aimed. The scattering was purely mechanical, velocity and density and time. And yet, not every star that reaches this point produces a visible explosion. Some of them, the very massive ones, or the ones where the conditions are slightly wrong, don't generate a shockwave that escapes. The star collapses, the core implodes, and the outside of the star, which a moment ago was still shining, simply goes dark. There's a lamp in the room where I usually read, a standing lamp, slightly too warm in colour, the kind that makes everything look like late afternoon regardless of the actual time, and I've developed the habit of noticing when it's on, not consciously, just peripherally, the way you register the presence of a sound you would only notice if it stopped. I think about that lamp sometimes when I think about N6946-BH1. The galaxy NGC 6946 sits about 22 million light-years away, in the direction of the constellation Cygnus. It's nicknamed the Fireworks Galaxy, which is either apt or ironic depending on what you're looking at, because it has an unusually high rate of observed supernovae, 10 in the last century alone, which is remarkable for a single galaxy. Astronomers watch it, have been watching it. It's the kind of galaxy that rewards attention because it tends to do things. In 2004, a red supergiant in NGC 6946 was catalogued, designated N6946-BH1. It was a massive star. Estimates put it somewhere around 25 solar masses, maybe more, and it was observed and recorded and filed as a known object. Its luminosity was measured. Its temperature was characterized. It was, in the language of stellar astronomy, a normal massive star in the late stage of its life. In 2009, something happened to it. Or rather, and this is the precise part, the part I want to stay with, persist. Something happened to the region of sky where it had been. The star briefly brightened, not dramatically, a modest optical transient, a faint flare that lasted a few months and then faded. Some papers from the time flagged it as potentially interesting. Then the flare faded and people moved on to other things. By 2015, when a team using the Large Binocular Telescope went back to look, as part of a survey specifically designed to search for massive stars that had disappeared, N6946-BH1 was gone. Not faded, not obscured, not hidden behind dust. The follow-up was thorough. Hubble observations, infrared imaging, multiple wavelengths, looking for any residual emission that would indicate the star was still there in some form. There was a faint infrared source at the location, consistent with a small amount of residual dust, and nothing else. The star had been there. Then there was a faint flare. Then the star was not there. No supernova. No bright explosion visible across millions of light years. No expanding nebula of ejected material. No pulsar. No X-ray source. No gravitational signature that would indicate a neutron star spinning at its former location. Just an absence. A place in the image where a star used to be and now wasn't. The most straightforward interpretations, and I want to be careful here, because straightforward interpretations in observational astronomy have a history of being revised. The most straightforward interpretation is that N6946-BH1 underwent a failed core collapse supernova. The core imploded, a black hole formed, but the shockwave that should have propagated outward and blown the star apart either never formed with sufficient energy, or stalled and was unable to revive, or, and this is one of the models, the black hole formed quickly enough to swallow the material before the shockwave could escape. The star fell into itself, quietly, with only a brief, modest flare to mark it. What caused the flare is debated. One possibility is that as the core collapsed, the outer envelope of the star, no longer gravitationally bound in the same way, suddenly unsupported from below, briefly expanded, maybe ejected some material before the whole thing was pulled inward. A kind of last exhale. Or it could have been shock heating from the neutrino burst, briefly depositing energy in the outer layers before the black hole swallowed the neutrino source. The models don't agree cleanly. What they do agree on is this. N6946-BH1 is not there anymore, and it did not go as a supernova. I find myself wanting to assign it a quality it doesn't have. A reticence maybe, or a reluctance. As if the star chose a quieter exit. Which is exactly the kind of thinking that astronomy is designed to cure you of, and I know that. And I'm mentioning it specifically because I think the impulse is interesting rather than because it's accurate. The star didn't choose anything. The physics of the particular mass, the particular core structure, the particular conditions at collapse, those determined the outcome. There was no decision, but the absence has a texture that's harder to process than an explosion would have been. With a supernova, there's something to see. The light arrives years, centuries later, depending on distance, and there's a record. The Crab Nebula is the remnant of a supernova observed by Chinese and Arab astronomers in 1054 CE. 1,000 years later, we can still see the expanding gas, the pulsar at the center, the detailed chemistry of what was ejected. The death left evidence. It left material in the universe that can be studied, touched by telescopes, mapped. N6946-B1 left a faint infrared smudge and a hole in a catalogue. The question of how often this happens, what fraction of massive stars collapse silently rather than exploding, is genuinely open. Some models suggest it could be a significant fraction. 10%, maybe more, of core collapses in certain mass ranges might result in failed supernovae. Others put the number lower. The observational surveys designed to find these disappearing stars are still running, still accumulating data, still trying to build a denominator for a fraction whose numerator keeps arriving as absences. You cannot easily count things that aren't there. The methodology is strange. You photograph a region of sky, catalogue every massive star you can resolve, and then you wait. You go back years later, and you look for the ones that are missing. You're searching for subtraction, looking for what the image no longer contains. There's something in that process, the structured, patient searching for absence, that I find unexpectedly affecting. Not zazz exactly. More like the feeling of going through an old address book and noticing a name you haven't thought about in years, and not knowing what happened to them, and being unable to find out. The survey is ongoing. More stars have been flagged as candidates. Massive stars that have faded or vanished without the expected supernova signature. Not many, but some, enough to make the question real. And each one is a place in a galaxy where something enormous used to be, and now the space simply holds whatever was already there. Gas, the faint light of background stars, a gravitational field that will persist for as long as the black hole persists, which is, well, longer than the galaxy will last in any form we'd recognize. The star is not missed by anything in NGC 6946. There is no frame of reference out there that registers its absence. Only here, from 22 million light-years away, do the images before and after carry any weight at all. The difference is only visible because someone was watching. That might be the strangest part of the whole thing. Whether a collapse produces a visible supernova or a silent disappearance, the question of what's left behind runs through the same narrow gate. It comes down to mass. A few solar masses difference in the surviving core, and the outcome changes entirely. Neutron star on one side, black hole on the other. The threshold between them is one of the places in physics where the universe's options genuinely run out. There's a kind of resistance you feel when you press two magnets together pole to pole. Not a wall exactly, more like a continuous insistence. The harder you push, the harder it pushes back, and the pushing back is not coming from anything you can see or touch, just from a field, from a geometry of force invisible to every sense except the one registered in your palm. You can hold the magnets close and feel the space between them doing something. Refusing. I keep coming back to that feeling when I think about neutron stars. A neutron star is not, and I want to be specific about this because the popular image is misleading. A neutron star is not simply a very small, very dense star. It isn't doing what stars do, it isn't fusing anything. There is no burning, no fusion chain, no energy generation of the kind that defines stellar life. The neutron star is a remnant. A corpse, if you want to be blunt about it, though corpse implies inactivity, and a neutron star is in many ways extraordinarily active. What it is, more precisely, is an object held in a state that shouldn't be stable by a force that barely tolerates the job. That force is neutron degeneracy pressure. When a stellar core collapses past the point where electron degeneracy can hold it, when the electrons are forced into the protons and the protons become neutrons, the resulting object is composed almost entirely of neutrons packed together at nuclear density. And neutrons, being fermions like electrons, obey the Pauli exclusion principle. Two identical fermions cannot occupy the same quantum state simultaneously. This is not a preference. It is not a tendency. It is a hard constraint built into the structure of quantum mechanics, and it generates a pressure, a resistance to compression, that has nothing to do with temperature or heat or any of the classical mechanisms that hold ordinary matter apart. Neutron degeneracy pressure is what holds a neutron star up. The object it holds up is, depending on mass, somewhere between 1.1 and 2.3 times the mass of the Sun, though the upper bound is uncertain, and that uncertainty matters, which I'll get to. It is approximately 20 kilometers in diameter. 20. The Sun is 1.4 million kilometers in diameter. The neutron star packs comparable mass, actually more in some cases, into a sphere you could drive across in about 12 minutes at highway speed. The density this implies is one of those numbers that language handles poorly. A teaspoon of neutron star material, and the unit teaspoon is absurd here, I know it's absurd, but it's the unit people use to make it feel touchable, would weigh somewhere around 4 billion tons. Not because the atoms are heavier, because there are no atoms, not in any ordinary sense. The neutrons are packed together at nuclear density, the density of an atomic nucleus, with no empty space between them. The electron clouds that give ordinary matter most of its volume gone. What's left is just nucleons touching. The surface gravity of a neutron star is approximately 200 billion times the surface gravity of Earth. If you were somehow standing on the surface, which you could not in any physical event survive approaching, a pebble dropped from 1 meter would hit the surface in about a microsecond, having accelerated to roughly half the speed of light. And all of that extraordinary density and gravity is being held in a marginally stable configuration by quantum stubbornness, by the refusal of neutrons to share states. It holds. For most neutron stars, it holds indefinitely. But there is a limit. The Tolman-Oppenheimer-Volkoff limit, worked out theoretically in 1939 by Robert Oppenheimer and George Volkoff, building on earlier work by Richard Tolman, is the neutron star equivalent of the Chandrasekhar limit for white dwarfs. It is the maximum mass a neutron star can have before neutron degeneracy pressure is insufficient to prevent further collapse. Above this mass, there is no known force in physics that can stop the contraction. The object collapses to a black hole. The problem, and this is the part that I find genuinely interesting, not as a rhetorical device, but because it reflects something real about the state of the physics, is that we don't know precisely where this limit sits. The theoretical value depends on the nuclear equation of state, the relationship between pressure, density, and temperature inside matter at nuclear densities. And the nuclear equation of state at the extreme densities in a neutron star interior is not fully known. The matter there is, it's not quite like anything we can produce or measure in a laboratory, not at those densities. We can constrain it from observations of known neutron stars, from gravitational wave measurements of neutron star mergers, from nuclear physics experiments. But the constraints leave a range. The TOV limit is somewhere between roughly 2.2 and 2.9 solar masses, maybe. Different models give different values. The most massive neutron star confidently measured sits at about 2.35 solar masses, which itself constrains the lower bound of the limit. It must be at least that, or that object wouldn't exist. But the upper bound remains uncertain. This means the threshold between neutron star and black hole is itself a fuzzy line. Not a crisp boundary, but a range. A region of mass where, depending on the specific physics of the core, the rotation rate, the thermal state, the outcome could go either way. The universe has a range of masses in which it hasn't fully committed to an answer. I want to be careful not to overstate the fuzziness. The range isn't enormous. We're talking about a span of maybe 1 solar mass, within which the outcome is uncertain. Outside that range, clearly below it, clearly above it, the physics is unambiguous. Neutron star on one side, black hole on the other. The uncertainty lives in a narrow corridor, but that corridor is where the most interesting question lives. What does it feel like? And I'm aware that feel is not a scientific term here, but stay with me. What does it feel like to be at that mass in that corridor? A neutron star core slightly too massive for degeneracy to hold, but only slightly. The pressure is there, the resistance is there, and gravity is pushing back against it with more force than the quantum stubbornness can answer. This is where the gradual nature of the failure matters. It's not instantaneous, not at these masses, not in the slow accretion scenario where a neutron star gains mass over time from a companion star. The degeneracy pressure doesn't suddenly switch off, it just becomes insufficient. Incrementally, the neutron star contracts slightly, the density increases, the pressure increases too. Degeneracy pressure does increase with density, but not fast enough, not quite fast enough to keep ahead of the gravity. And then there's just no more resistance left to give. The last defense, The last physical thing the universe can construct to push back against gravity runs out. Not dramatically, just quietly, incrementally, runs out. What forms in its place is not a denser neutron star. It's not a new phase of matter we haven't discovered yet. It's not, as far as we can tell, anything that can be described in terms of matter at all at the centre. What forms is a region of space-time from which nothing, not matter, not light, not any signal of any kind, can escape. A black hole. The threshold between the two is a few solar masses, the distance between the last thing physics can build and the thing that physics as we practice it cannot fully describe, a few solar masses. That's a thin door. On the other side of that door, the question changes from what collapsed to what remains. And what remains is, in some ways, the strangest part of all. Not because of what it does, but because of what it is, or isn't. The word whole is the wrong word. It was always the wrong word. Close your eyes for a moment and pay attention to the directions available to you. Forward, back, left, right, up, down, and tamom. Always forward, never back. A direction you travel whether you choose to or not. These are the directions the universe gives you. 6 spatial, 1 temporal, and the temporal one is non-negotiable. You cannot stop the moving through time. You can only move through it at different rates depending on your velocity and the gravitational field you're sitting in, but you cannot reverse it, and you cannot stand still in it. It flows. This is the background geometry of your life. You probably don't think about it. Why would you? It's just what space is. A black hole is a place where this geometry breaks. Not dramatically, not with any visible seam or boundary you could feel as you crossed it under certain conditions, but structurally, fundamentally, in a way that makes the region inside a black hole not just a different place, but a different kind of place. One where the directions available to you have been rearranged in a manner that no velocity, no force, no engine can compensate for. Me try to be precise about this because I think the usual descriptions get it slightly wrong, and the wrongness matters. The standard image of a black hole, the drain, the whirlpool, the thing pulling everything in, implies that a black hole is a location with a very strong gravitational pull, and if you get too close you get sucked in like water near a drain, and if you could just go fast enough you could escape. This is wrong in a specific way. It's not wrong about the strength of the gravity, it's wrong about the structure of what's happening. The event horizon, the boundary of a black hole, the threshold beyond which nothing returns, is not a wall. It doesn't exert force on you as you cross it. A person falling freely into a sufficiently large black hole would cross the event horizon without feeling anything unusual at the moment of crossing. No alarm, no resistance, no sensation marking the transition. What changes at the event horizon is geometry. Outside the event horizon, all possible future directions, every path through space-time that you could take, include directions that lead away from the black hole. You can, in principle, fire a rocket and escape. The inward direction is one option among many. Inside the event horizon, the curvature of space-time has become so extreme that all possible future directions, every path through space-time available to you, including the path of a light beam fired directly outward, curve back inward. The inward direction isn't a pull anymore, it's the only direction that exists. This is what I mean by geometry breaking, not the force getting stronger. The directions getting fewer. Time itself inside the event horizon points toward the singularity the way time outside points toward the future. You cannot avoid the singularity for the same reason you cannot avoid tomorrow. The word whole is wrong. I've known this for a long time and it still bothers me in a low-grade, slightly irrational way. The word implies an opening, a cavity, an empty space you could in principle look into from the outside and see through to the other side. None of that is accurate. A black hole is not a hole in space. It is a region of space, fully occupying the volume it occupies, doing nothing so simple as being absent, from which the causal structure of space-time has been severed from the outside universe. Things can enter, nothing can leave. Not because leaving is difficult, but because inside the event orbit, and there is no direction that leads to outside. Disconnected. That's the more accurate word, I think, though disconnected doesn't capture it either, not fully. The interior of a black hole is causally disconnected from the exterior. Whatever happens inside cannot send any signal, any light, any particle, any gravitational ripple outward across the boundary. The inside and outside are in the same universe in the sense of being part of the same space-time manifolds, technically, mathematically, but no information can pass from one to the other in the outward direction. This is where the information paradox lives, though don't want to pull that thread too hard tonight. The short version: quantum mechanics insists that information cannot be destroyed. General relativity combined with the causal structure of black holes seems to imply that anything falling into a black hole takes its information with it into a region permanently sealed from the outside universe. Stephen Hawking showed in 1974 that black holes do slowly radiate, Hawking radiation, a quantum effect at the event horizon, and that over an extraordinarily long time they lose mass and eventually evaporate. But whether the information that fell in is preserved in that radiation, and if so how, is a question that has occupied theoretical physicists for 50 years without a fully satisfying resolution. I'm going to leave it there, not because it isn't interesting, it's one of the most interesting open questions in physics, but because it pulls toward a different chapter than this one. Tonight I want to stay with the geometry, the singularity at the centre of a black hole, or more precisely, at the endpoint of every infalling trajectory inside the event horizon, is where general relativity's description breaks down. The equations produce infinite curvature, infinite density, and physicists generally treat this as the signal that the theory is incomplete, rather than as a literal description of what exists there. Quantum gravity, a theory we don't fully have yet, is expected to modify the picture at the Planck scale, the smallest meaningful length, in physics. What actually happens at the centre of a black hole, in the physical reality rather than the mathematical model, is genuinely unknown. The singularity might not be a point. It might not be a place in any spatial sense. In a rotating black hole, which is the realistic case because stars rotate, and conservation of angular momentum means the black hole inherits that rotation, amplified enormously by the collapse. The singularity is modelled as a ring rather than a point, a Kerr black hole, named for Roy Kerr, who found the exact solution to Einstein's equations for a rotating mass in 1963. The geometry is richer, stranger, and in some mathematical senses even more troubling than the non-rotating case. But the event horizon remains, in all cases, the practical boundary, the thing that makes a black hole, not the singularity. That's interior, inaccessible, unknown. The event horizon is the surface, if you can call it a surface, at which the causal disconnection becomes complete. From outside, a black hole is almost nothing. Gravitationally, it behaves like any other mass. If the Sun were somehow replaced by a black hole of equal mass, the planets would continue orbiting exactly as they do now. Nothing would be pulled in that wasn't already on a trajectory toward it. The darkness, the silence, the causal severance, those are interior properties, and the interior is, by definition, unreachable by any observation we can make. What we see is the effect on the space around it. Gas heated to millions of degrees in the accretion disk, glowing in X-rays. Stars orbiting the galactic center in paths that only make sense if something with 4 million solar masses is sitting there, dark and quiet, influencing everything without being seen. The first image of a black hole's shadow, the region where light is bent so severely that the black hole silhouettes itself against its own glowing accretion disk. Captured by the Event Horizon Telescope in 2019, a blurred orange ring around a central darkness that was, for all its blurriness, genuinely a photograph of where light couldn't escape. We saw the hole-shaped absence of light. We didn't see the hole. We cannot see the hole. It exists with the thoroughness that makes observation impossible, and it does this not through opacity or distance, but through the structure of causality itself. No signal originates there. No information leaves. The interior is not hidden from us in the way a distant object is hidden. It is hidden in a more complete sense, structurally severed, causally sealed, present in the universe without being accessible to it. And there are, conservatively, tens of millions of them in the Milky Way alone. Stellar mass black holes scattered through the galaxy, dark and quiet, orbiting the galactic center the way everything else does, influencing the gas and stars around them through gravity, giving away their presence only when they happen to be consuming something. Most of them aren't. Most of them are just there, in the dark, doing the thing gravity has always wanted to do, and doing nothing else. The universe made them without ceremony, without intent, and they persist without either. The sun will not become one of them. Not because the physics doesn't apply, the physics applies to everything, but because the sun is, in the specific numerical sense that matters here, too small, too ordinary, too much itself. That ordinariness is the next thing worth sitting with. The light coming through a window in the morning has already been travelling for a long time. 8 minutes from the sun's surface to wherever you are. That part most people know. But the 8 minutes is almost the least interesting part of the journey. Before the photon reached the surface, before it had open space to cross, it spent somewhere between 10,000 and 100,000 years. The estimates vary depending on how you model the random walk, moving through the interior of the sun, bouncing, scattering, absorbed and re-emitted, nudging outward through plasma so dense that the mean free path of a photon, the average distance it travels before hitting something, is about a centimetre. A centimetre in a star 1.4 million kilometres across. The light on the floor this morning left the sun's core before anatomically modern humans existed. Before the last ice age, before the extinction of the woolly mammoth, before Stonehenge, before every civilization whose name we know. It spent all of that time working its way outward through the sun's interior, and then crossed 150 million kilometres of vacuum in the time it takes to make a cup of tea, and came through your window. I find that genuinely hard to hold. It doesn't resolve into anything manageable. I just keep turning it over. The sun is, in the taxonomy of stars, ordinary. Aggressively, almost defiantly ordinary. It is a G-type main sequence star, G2V if you want the full classification, which places it firmly in the middle range of stellar masses, temperatures and luminosities. Not the biggest, not the brightest, not the hottest. Somewhere around 90% of stars in the Milky Way are less massive than the Sun, which pushes it toward the upper end of the common range, but only toward. It is not an outlier in any direction. It is the median made slightly warmer. This ordinariness is, I think, underappreciated. What the Sun's mass means, specifically, The fact that it sits at approximately 1 solar mass, which sounds tautological but isn't, is that everything downstream in its life is determined. The fusion rate, the surface temperature, the luminosity, the lifespan, the endpoint, all of it falls out of the mass. Stars are, in a meaningful sense, almost entirely their mass. The composition matters at the margins. The rotation rate matters for some things, but mass is the overwhelming determinant of what a star is and how it dies, and the Sun's mass, 1 solar mass, not 20, not 50, not 100, places it firmly on the path that leads nowhere near a black hole. The core of the Sun right now is running the proton-proton chain. 4 hydrogen nuclei, protons, go through a sequence of reactions and emerge as 1 helium-4 nucleus. The mass of the helium nucleus is slightly less than the combined mass of the 4 protons. That missing mass, about 0.7% of the original, is converted to energy according to E equals mc squared, and it is this energy, continuously released at the rate of about 3.8 times 10 to the 26th power watts, that holds the Sun up against its own gravity and incidentally makes the Earth habitable. The proton-proton chain is not a fast reaction. This is, I have an odd affection for this fact, this is actually a feature rather than a flaw. The first step in the chain, where 2 protons fuse to form a deuterium nucleus, requires one of the protons to undergo beta plus decay mid-collision, converting to a neutron. Beta decay is mediated by the weak nuclear force, which is weak on purpose, or rather is weak as a matter of physics, not design. And this weakness makes the reaction extremely unlikely at any given collision. A proton at the Sun's core will, on average, wait about 9 billion years before successfully completing this first step with a collision partner. 9 billion years per proton per successful reaction. The Sun is not burning fast. The Sun is burning with an almost absurd restraint, because the weak force bottleneck makes the first step of fusion so improbable that the fuel lasts not millions but billions of years. A star more massive than the Sun runs hotter and denser, and the higher temperature and density push it toward fusion pathways, the CNO cycle, that are faster and less bottlenecked. It burns through its fuel orders of magnitude more quickly. A star of 25 solar masses might live only a few million years. The Sun, because of its modest temperature and its dependence on the slow proton-proton chain, gets 10 billion. It has used roughly half of that. There's a wood-burning smell that comes through the window sometimes on cold mornings from somewhere nearby. A fireplace, probably, in one of the houses on the street, and I notice it sometimes when I'm thinking about the Sun's core because the contrast is almost funny. A fireplace combusts fuel through a chemical reaction, which operates at the level of electron shells, which involves energies in the range of a few electron volts per reaction. The Sun's core fuses nuclei, which operates at the level of the strong and weak nuclear forces, which involves energies millions of times higher per reaction. And yet, the fireplace burns through its fuel in hours. The Sun has been burning for 4.6 billion years and is not halfway done. That is what it means to be 1 solar mass. To be exactly ordinary enough that the physics gives you 10 billion years at a temperature and pressure that is, by stellar standards, restrained. The equilibrium the Sun maintains, the hydrostatic equilibrium we talked about at the beginning, is not passive. I want to correct that assumption because I think it's a common one. The Sun is not simply sitting in a stable state that requires no maintenance. The fusion in the core is continuously and actively pushing outward, and gravity is continuously and actively pulling inward, and the balance between them is dynamic, responsive, self-correcting, constantly adjusted. The Sun breathes thermally. If the core gets slightly too hot, the star expands slightly, the density drops, the fusion rate drops, the pressure drops, gravity wins a little ground, the density increases, the fusion rate ticks back up. It regulates itself across timescales of thousands of years. This has been happening without interruption for 4.6 billion years. The sun that illuminated the Cambrian seafloor, when the first complex animal life was diversifying in the oceans, when trilobites were new, was the same sun doing the same thing, maintaining the same balance. The sun that shone on the first land plants, the first forests, the first dinosaurs, the first hominids chipping flint at a riverbank. The same process, the same equilibrium, the same quiet fusion, in a core that photons take 100,000 years to escape. There is something in that continuity that I find, I want to say moving, but that's not quite it. It's more like the feeling of something being reliable, in a way that reliability doesn't normally achieve. The sun has been there, continuously without pause for longer than the Earth has existed. Before the Earth, before anything we know. It was already doing this when the solar system was still a disk of gas and dust, and it will be doing this, in some form, for another 5 billion years. One solar mass. Not enough to reach the carbon-burning threshold after helium runs out. Not enough to build an iron core. Not enough to cross any of the thresholds we've spent the last several chapters climbing through. The sun's going to exit this story quietly. Not through catastrophic collapse, not through a supernova, not through any of the events that transform stellar death into a black hole. Its path branches off earlier, turns away from that sequence entirely, and takes a different, slower, gentler route toward a different kind of end. That route starts with what happens when the hydrogen is finally gone, and that, the swelling, the expansion, the long billion-year departure is the next thing to sit with. There's a particular quality to late afternoon light in autumn. The angle of it, the way it comes in low and spreads across a floor or a wall in a colour that's almost amber, almost gold, something you can't quite name, that I've never been able to fully describe without it sounding like I'm trying too hard. It just sits there, that light, on whatever surface it finds, warm and unhurried, and then it goes. The sun is going to do something like that. Eventually. Over a period of time so long that the word eventually loses almost all its meaning. In approximately 5 billion years, the hydrogen in the sun's core will be genuinely exhausted. Not running low, the sun is not currently running low, it has roughly 5 billion years of core hydrogen remaining, which is more time than the Earth has currently existed, but finished. The core will have converted its hydrogen to helium across such a vast stretch of time that the process will have consumed the fuel completely, and the fusion that has been generating outward pressure since before the solar system formed will simply stop. What happens next is not a collapse, not immediately. This is the assumption I want to correct early, because the sequence feels counterintuitive. The core stops generating energy, and the sun gets bigger, not smaller, bigger. Here's the actual sequence because it matters and it's interesting and it takes a moment to sit with. When the core hydrogen is exhausted, the core, now composed primarily of helium, contracts under gravity. This contraction releases gravitational energy which heats the region immediately surrounding the core. That shell of hydrogen just outside the helium core gets hot enough to begin fusing. Shell hydrogen burning ignites, and the energy output of this shell burning is paradoxically higher than the core burning it replaces. The geometry of the shell, and the higher temperature driving it, produce more energy than the core was generating before. More energy means more outward pressure, More outward pressure means the outer layers of the Sun, the enormous volume of gas above the shells, respond by expanding. The Sun swells, not quickly, not suddenly, but continuously, over hundreds of millions of years, pushing its outer atmosphere outward into space. The surface temperature drops as the same luminosity spreads over a vastly larger area. A larger sphere radiating the same total power is cooler at any given point on its surface. The colour shifts, the Sun reddens. This is the red giant phase. It is, in the scheme of stellar lifetimes, not a brief event. The red giant phase for a star like the Sun lasts roughly 1 billion years. 1 billion years of slow, steady, almost inconsiderate expansion. Inconsiderate in the sense that it has no interest in what it's expanding into, no regard for any of the geometry it's rewriting, during which the Sun's outer atmosphere grows from its current radius of about 700,000 kilometers to somewhere between 100 200 times that. Maybe more, depending on which models you trust and at what stage of the evolution you're measuring. At peak expansion, the Sun's surface will be approximately where the Earth's orbit currently is. I want to stay with that for a moment and not rush past it, because it's the kind of fact that the mind tends to file as dramatic and move on from, and I think moving on from it too quickly loses something. The orbit of Earth, the path Earth traces around the Sun right now, the path that has existed in roughly its current form for 4.5 billion years, the path that defines the distance at which liquid water is possible on a rocky surface, the path that in some real sense defines what Earth is. That orbit sits approximately where the Sun's outer atmosphere will eventually reach. Whether Earth is actually engulfed is, interestingly, not fully settled. The Sun will lose a significant fraction of its mass during the red giant phase, shed outward by stellar winds that intensify as the star expands. And as the Sun loses mass, its gravitational grip weakens, which causes the planet's orbits to expand outward. Earth's orbit may migrate outward fast enough to stay ahead of the expanding surface. Some models say yes, it escapes engulfment. Others say the orbital migration isn't quite fast enough and the outer atmosphere catches it. The difference comes down to the rate of mass loss, which is difficult to model precisely. What is not uncertain is that Earth will be uninhabitable long before any question of engulfment becomes relevant. As the Sun brightens during its gradual main sequence evolution, it is already about 30% brighter than it was when life first appeared on Earth, and will continue brightening. The habitable zone moves outward. In roughly 1 billion years, maybe a little more, the Sun will be bright enough that the Earth's surface temperature will have risen to the point where the oceans begin to evaporate in earnest. Not overnight, not in a century. Gradually over geological time, the water cycle destabilizes. Hydrogen escapes to space, the oceans thin, the climate enters a feedback loop it doesn't exit. 1 billion years. That's approximately how long complex life has left on Earth, in the broad strokes, before the Sun simply becomes too much. I find myself unable to feel this as a loss in any direct way, and I've thought about why. I think it's because 1 billion years is not a timescale the human emotional apparatus was built to process. Our grief scales to things we can imagine losing, people, places, years. 1 billion years is not years in any emotionally accessible sense. It is a different category of time, the kind that only mathematics and geology can navigate. And both of them navigate it without feeling anything about it, which might be fine. Maybe some facts are meant to be known rather than felt. I was standing outside once on a clear night, cold enough that I'd been inside too long, and the sudden temperature of open air had that particular sting to it, the kind that makes you aware of your face as a surface, and I was looking at the moon, which was full and very bright, and I was thinking about the fact that the moon is slowly receding, moving away from Earth at about 3.8 centimeters per year. In the distant past it was much closer, and the tides were enormous, and the days were shorter. In the distant future it will be farther, and the tides will be weaker, and the days will be longer. The moon you see on any given night is a snapshot of a slow process that has been running for billions of years in one direction and will continue in the same direction until something else intervenes. The sun's expansion is like that, not a moment, a process, slow enough that no observer within it would notice the change across a lifetime or 1,000 lifetimes. The change is only visible across geological time, across the kind of duration that rock records and isotopes encode, and astronomers reconstruct from stellar models. The sun will swell. The inner solar system will be rewritten. The Earth's surface, the specific, particular, improbable surface where liquid water pooled and chemistry became biology and biology became everything we know, will be returned to rock and then to vapor, and then to the outer atmosphere of a red giant star that will not know or care what it has passed through. This is not tragedy. I want to be careful about that. Tragedy requires stakes that belong to the event itself, and the sun's expansion has no stakes. It is a physical process, following from a mass and a fuel supply and the laws of nuclear physics and gravity. It was always going to happen. It is happening right now, very slowly, in the sense that the sun is gradually brightening and the clock is running. There is no intervention, no alternative, no version of this story where one solar mass of hydrogen-burning gas lasts forever. What there is, instead, is time. More time than any human frame of reference accommodates. Enough time that everything we have been, and everything we might become, and everything that might come after us on this planet or elsewhere, fits inside the interval between now and the moment the oceans begin to fail. 1 billion years. The red giant phase beginning 5 billion years after that. The sun, in other words, is nowhere near done. When the red giant phase ends, when the helium ignites and burns, and the outer layers are finally expelled, what remains at the center is not nothing. It is something specific, small and dense and very, very hot, and it will glow for longer than the current age of the universe before anyone could reasonably call it dark. There's a cast iron pan in my kitchen that holds heat in a way that other pans don't. You take it off the burner and it sits there on the counter, still ticking occasionally as the metal contracts, and if you hold your palm a few centimeters above the surface you can feel the warmth radiating upward for a long time after the flame is gone. Not burning, not generating anything, just releasing what it absorbed, slowly, on its own schedule, indifferent to the fact that the cooking is finished. A white dwarf is something like that. Not a star anymore, in the sense that matters, not fusing, not generating energy through any nuclear process. The fusion stopped when the outer layers were expelled, when the red giant phase ended and the helium shell burned through, and the sun's outer atmosphere, the enormous volume of gas that had expanded outward across hundreds of millions of years, was finally pushed away by radiation pressure and stellar winds into the surrounding space. That departure, the expulsion of the outer layers, is the actual death. The planetary nebula, the glowing shell of ionized gas expanding outward through the interstellar medium, is the obituary. What remains at the center after that departure is not a dying star. It has already died. What remains is a white dwarf, the core, the inner region of the sun that was never part of the extended atmosphere, the part that was always hot and dense and doing structural work, stripped bare, exposed to open space, no longer covered by the weight of the layers above it. It is composed primarily of carbon and oxygen. These are the products of the helium fusion that ran during the Sun's later life. Helium nuclei fused into carbon through the triple alpha process, some of that carbon fusing further with additional helium to produce oxygen. Carbon and oxygen layered and mixed, comprising the bulk of what the Sun will leave behind. The mass of this remnant will be roughly half the Sun's current mass, the other half having been lost to stellar winds and the final expulsion. Its diameter will be approximately that of Earth, maybe slightly smaller. The density this implies is extraordinary by any normal measure. A cubic centimetre of white dwarf material weighs somewhere around a ton, but it is not, in the scheme of stellar remnants, the most extreme. Neutron stars are far denser. Black holes are a different category entirely. The white dwarf sits in the middle of the remnant hierarchy, denser than anything on Earth, less dense than the objects we spent the first half of this script building toward. What holds it up is not fire. This distinction matters, and I want to hold it clearly for a moment. Ordinary stars are held up by thermal pressure, the outward force generated by hot gas, by the energy of fusion heating the core and pushing against gravity. Thermal pressure is temperature dependent. It requires heat. It requires burning. A white dwarf has neither. The fusion is over. The core is hot, initially extremely hot, perhaps 100,000 Kelvin at the surface immediately after formation. But that heat is residual, inherited from the stellar life that preceded it. It is not being replenished. The white dwarf is held up by the electron degeneracy pressure, the same quantum mechanical effect that held up the stellar core before the collapse in a massive star, the Pauli exclusion principle, the refusal of electrons to share quantum states, operates here, but sufficiently. The white dwarf's mass is below the Chandrasekhar limit. The electron degeneracy pressure is enough. It holds without needing to generate energy, without burning anything, without any process that requires the star to be alive. It simply holds the way a rock holds its shape, not because it's doing anything, but because its internal structure resists compression. That resistance will not fatigue. Electron degeneracy pressure doesn't weaken over time. It doesn't depend on anything that runs out or degrades. As long as the white dwarf's mass stays below the Chandrasekhar limit, and it will, unless it accretes significant mass from a companion star, it will remain stable indefinitely, not for a long time, indefinitely. The only thing that will change is the temperature. The white dwarf will cool as it has no internal energy source, so the heat it radiates into space comes directly from its thermal reservoir, from the stored heat of its previous stellar life, slowly leaking outward across the surface. This is the cast iron pan sitting on the counter. The heat leaves at a rate determined by the surface temperature and the surface area, and as the temperature drops, the cooling slows, because cooler objects radiate less efficiently. The cooling curve is not linear, it stretches. The timescale for a white dwarf to cool to black, to reach a temperature indistinguishable from the cosmic background, to become what's theoretically called a black dwarf, is somewhere in the range of a quadrillion years. 10 to the 15th power years. Maybe more, depending on the mass and composition. The current age of the universe is approximately 13.8 billion years. A billion is 10 to the power of 9. The cooling timescale is 1,000,000 times longer than the current age of the universe. This means there are no black dwarfs. Not one. Not anywhere. The universe is too young for any white dwarf, even the first ones formed shortly after the earlier stars died, to have cooled to that point. Every white dwarf that has ever formed is still radiating, still warm, still working through its thermal inheritance at whatever rate its surface temperature permits. I find this genuinely strange in a way I can't fully articulate. The end point of the sun's life, the cold, dark carbon remnant that is theoretically where this all ends, doesn't exist yet. Not because the sun hasn't reached it, because nothing has. The universe hasn't been running long enough for its own stellar remnants to finish cooling. The final state of a white dwarf is a prediction, not an observation. It is the expected conclusion of a process that is everywhere and in every case still in progress. The sun will become a white dwarf in roughly 7 billion years, and then it will cool. For longer than the universe has currently existed, for longer than the universe will exist before the last stars form and die. On a timescale so extended that the word future loses any useful meaning long before it ends, carbon and oxygen, held by quantum stubbornness, cooling in the dark. There's no conclusion that fits comfortably at the end of that picture. The process doesn't have a moment where you'd say, there. That's the end. It just continues gradually, the temperature dropping degree by degree, the radiation weakening, the object becoming less and less distinguishable from the cold space around it, until the distinction disappears entirely. Not violently, not dramatically, the same way the warmth leaves a surface when the source is gone. The difference between the sun's ending and a black hole's ending comes down to a number. One number, roughly. The mass the sun was born with, held against the mass that changes everything downstream. The next chapter is about that gap, not as tragedy, not as luck, just as arithmetic that happens to determine the shape of a star's entire existence. 20. That's roughly the number. 20 solar masses, give or take depending on the model, depending on the metallicity of the star, depending on how much mass it loses to stellar winds during its life, is approximately the threshold below which a star does not produce a black hole at the end of its life. Above it, the conditions exist for a core massive enough after collapse to exceed the neutron degeneracy limit. Below it, they don't. The sun is one solar mass. So the gap between what the sun is and what a star needs to be to end as a black hole is a factor of 20. Not a small gap, in the sense that 20 times anything is genuinely larger than the thing itself, but not an astronomical gap either, not in the literal sense, not in the context of a universe that contains stars of 100 solar masses, 200, possibly more. 20 it's a specific number. Not round in any meaningful way, not a tidy boundary the universe drew deliberately. Just the number that falls out of the physics when you ask at what mass the iron core after collapse reliably exceeds the Tolman-Oppenheimer-Volkoff limit. I was holding a litre of water once, just a full water bottle, the plastic kind, sitting in my hand while I was reading, and I kept moving it slightly, feeling the weight shift, thinking about how a litre of water weighs a kilogram, 1 kilogram, and the sun weighs 2 times 10 to the 30th power kilograms, and a star of 20 solar masses weighs 20 times that. And the difference between one of those and 20 of those, the difference that determines whether you get a white dwarf or a black hole, whether you get electron degeneracy or causal disconnection, whether you get billions of years of quiet cooling or a collapse that rewrites the local geometry of space-time, is just multiplication, just a factor, just arithmetic applied to a cloud of gas that happened to condense with a certain amount of material in it 4.5 billion years ago, or 10 billion years ago, or whenever. Mass is not in itself complicated, it's just stuff. How much stuff? The word mass covers an enormous conceptual territory in physics. Inertial mass, gravitational mass, rest mass. The Higgs mechanism. The relationship between mass and energy. But at the level we're talking about here, for stellar evolution, it is simply the quantity of material the star was born with. The initial condition. The number written at the top of the calculation before anything else runs. Everything downstream is determined by that number. The fusion rate, the core temperature, which burning phases occur and which don't, the duration of each phase, whether the carbon burning threshold is crossed, whether an iron core forms, whether the iron core after the collapse is massive enough to defeat neutron degeneracy, whether a black hole forms or a neutron star, or for stars like the Sun, whether the core never gets past helium burning at all before the outer layers detach and drift away. One number, written at the start, everything else follows. I want to resist something here. The framing that creeps in naturally, almost unavoidably, where the black hole outcome gets treated as the more significant one, the more dramatic ending, the more interesting fate, as if 20 solar masses produces a death worth something that one solar mass doesn't. I've noticed this framing in myself, actually, and I'm not sure it's right. Both outcomes are consequences of the same physics. Both are what happens when a star exhausts its fuel and gravity has its way with what remains. The black hole is more extreme, certainly, the physics more violent, the remnant more structurally unusual. But extreme is not the same as meaningful. The Sun's white dwarf is not a consolation prize. It is what one solar mass of hydrogen and helium does when it's finished, that's all. And there's something in the plainness of that. Something in the fact that the Sun will burn for 10 billion years, expand for a billion more, shed its outer layers quietly, and leave a carbon-oxygen remnant that will cool for longer than the universe has currently existed. That doesn't need the comparison to a black hole to be worth sitting with. It's worth sitting with on its own. The timescales alone are worth sitting with. The fact that electron degeneracy pressure, a quantum effect with no classical equivalent, will hold the remnant stable indefinitely, that's worth sitting with. The fact that the light on your floor this morning was generated in the Sun's core before anatomically modern humans walked this planet, that's worth sitting with. The black hole is the more dramatic story, but the Sun's story is longer. 5 billion years of hydrogen burning still ongoing, then helium, then the expansion, then the nebula, then the white dwarf, glowing on stored heat, slowly cooling through timescales the universe hasn't reached yet. From here, from now, from this specific moment on a planet orbiting a G-type main sequence star at 1 astronomical unit, the story is nowhere near at its end. The number is 20. The Sun is 1, and the distance between those two numbers contains everything. The iron core that didn't form, the shockwave that won't propagate, the event horizon that won't exist, and in their place, a long, quiet, undramatic burn that has been running since before the Earth was solid, and will be running long after anything on its surface could notice. You're sitting right now inside that story, under that light, on a planet warmed by a star that is, by every stellar standard, unremarkable, and that will continue being unremarkable, stably and reliably, and without catastrophe for longer than the mind can genuinely hold. That's not a small thing. It's just not a loud one. There's a specific quality to a room with every light off. Not just dark. Dark is just the absence of photons, a physical condition. What I mean is the particular texture of a space you know well, that you've moved through in daylight 1,000 times, reduced to something navigable only by memory and the faint geometry of shapes against slightly less dark shapes. Everything still there, nothing illuminated. the room unchanged and unrecognizable simultaneously. The universe is heading towards something like that. Not soon. Not in any timescale that connects to anything we've discussed so far in this script. The sun's 10 billion year lifespan, which felt large when we were inside it, is, in the context of the universe's future, essentially the opening sentence. What comes after is so extended, so empty of the processes that define the universe we know, that the numbers require a different relationship with time than the one our minds normally carry. Let's stay close to the physics and move outward carefully. Right now, the universe is in what cosmologists call the Stelliferous era, the era of stars. It began with the first stars igniting a few 100 million years after the Big Bang, and it will end, not with a bang, not with any discrete event, when the last star exhausts its fuel and goes dark. That ending is not imminent. The universe is currently about 13.8 billion years old. The Stelliferous era is expected to last somewhere between 1 and 100 trillion years, depending on how long the smallest, most fuel-efficient stars, the red dwarfs, manage to keep burning. Red dwarfs are not dramatic stars. They are small, cool, dim, slow-burning, the kind of stars that receive almost no attention in popular astronomy because they don't explode spectacularly, or produce black holes, or generate the conditions for complex chemistry in their immediate vicinity. But they burn hydrogen so slowly, at such low temperatures and pressures, that a red dwarf of minimum mass might sustain fusion for 10 trillion years. 10 trillion. The sun's entire lifespan fits inside that number 1,000 times. When the last red dwarf finally exhausts its hydrogen and fades, and this will happen eventually because all fuel runs out, the Stelliferous era ends. No more star formation. The gas reservoirs that have been feeding new stellar generations across hundreds of billions of years will be depleted, locked up in remnants or dispersed too thinly to collapse. The sky, for anyone or anything that existed to observe it, would contain no stars, only remnants. White dwarfs cooling across timescales we've already discussed. Neutron stars spinning in the dark, slowing gradually as they radiate energy through magnetic dipole radiation, their pulses becoming longer and less frequent over millions of years. And black holes, sitting at the centres of what used to be galaxies, having long since consumed whatever was close enough to accrete, now simply present. Massive. Patient. This is the degenerate era. It is, in a specific sense, extraordinarily quiet. Not empty, not yet, but quiet in the way a city is quiet at 4 in the morning. The infrastructure still present, the structure still standing, but nothing actively running. The white dwarfs glow faintly on residual heat, cooling degree by degree across the quadrillion-year timescales we touched on in the last chapter. Neutron stars cool too, more quickly initially, their surfaces dropping from the millions of Kelvin of their formation to something much colder across millions of years, then continuing to cool more slowly. Occasionally, but rarely, on these timescales, a white dwarf might accrete enough basalt from a passing object across the Chandrasekhar limit and explode as a Type 1, a supernova, a brief flare of light in an otherwise dark sky. But these events become rarer as the remnants disperse and the distances between objects grow. The galaxies themselves will have changed by this point, or rather, the structures we call galaxies will have dissolved. Over timescales of roughly 10 to the power of 19 to 10 to the power of 20 years, gravitational interactions between stellar remnants gradually redistribute energy through a process called two-body relaxation. Close encounters between objects transfer momentum Some objects sink inward, some are flung outward. Eventually most of the mass in a galactic structure either falls toward the central black hole or gets ejected entirely into intergalactic space, drifting outward on trajectories that will never bring them back. What was a galaxy becomes a sparse scattering of remnants around a supermassive black hole, and then even that scattering thins as objects are slowly ejected or consumed. And then, on timescales that I want to be honest about, because we are now in territory where the physics is well grounded, but the extrapolation is extreme. We enter the black hole era, everything is gone except the black holes. All the white dwarfs have cooled to black dwarfs by now, or they haven't quite, depending on the mass. The most massive white dwarfs cool faster, the least massive might still be faintly warm. But for practical purposes, the degenerate remnants have exhausted their thermal energy. The neutron stars have cooled to within a few degrees of the cosmic background temperature, dark and cold and spinning very slowly. The black holes remain. Stellar mass black holes. Intermediate mass black holes. The supermassive black holes that once anchored galaxies, now floating in a universe that no longer has galaxies. They are the last massive objects. The last things in the universe with significant gravitational influence. And they are, slowly, almost incomprehensibly slowly, evaporating. Hawking radiation. The quantum mechanical process that Stephen Hawking derived in 1974, showing that black holes are not perfectly black, that the quantum vacuum near the event horizon produces pairs of particles, one of which escapes and one of which falls in, with the net effect that the black hole loses mass over time. The rate of this evaporation is inversely proportional to the mass of the black hole. Smaller black holes evaporate faster, larger ones slower, much slower. A stellar mass black hole, say 10 solar masses, would take approximately 2 times 10 to the 67th power years to evaporate completely through Hawking radiation. That number has 67 zeros. To give it a handhold, the current age of the universe is 1.38 times 10 to the 10th power years. The evaporation time is 57 orders of magnitude longer than the current age of the universe. It is not a long time in the way that a red dwarf's 10 trillion year lifespan is a long time. It is a long time in a different category entirely, a timescale that shares almost no conceptual space with anything in the previous 12 chapters. A supermassive black hole, say the 4 million solar mass object at the centre of the Milky Way, would take roughly 10 to the power of 83 years. And the largest black holes in the universe, the ones at the centres of the most massive galaxies, measured in billions of solar masses, those would take perhaps 10 to the power of 100 years. 10 to the power of 100. A googol. A number that exceeds the estimated number of atoms in the observable universe by an enormous margin. A duration so extended that the word year, used to measure it, is almost an act of category error. During all of this evaporation, across all of these incomprehensible timescales, the Hawking radiation produced is thermal radiation, carrying energy outward into the universe. As the black hole loses mass, it gets slightly hotter, radiates slightly faster, loses mass slightly faster, in a feedback that remains almost imperceptible for most of the evaporation time, and then, in the final fractions of a second before the black hole reaches negligible mass, accelerates into a burst of high-energy radiation. The last moments of a black hole are bright, a flash of gamma rays, and then nothing. Nothing where something massive had been. No remnant, no object, just the space that used to contain a black hole, now containing only the faint thermal glow of the radiation it spent 10 to the power of 100 years emitting. And after the last one goes, I want to be careful here, because this is where the physics I can describe confidently ends and the extrapolation becomes genuinely uncertain. After the last black hole evaporates, the universe contains, as far as current physics can determine, only the products of that evaporation: photons, neutrinos, electrons and positrons in dilute concentrations, slowly annihilating into more photons. The cosmic background radiation stretched now by the expansion of the universe to wavelengths so long they are essentially undetectable. A temperature so close to absolute zero that the distinction is formal rather than physical. No structures, no gradients significant enough to do thermodynamic work. No free energy available to drive any process. Just the dark, and the slow, cold expansion, and whatever physics exist at scales and conditions we have no way to probe from here. Whether this is truly an ending, whether something else follows, whether the universe cycles, whether the low entropy initial condition that started everything 13 billion years ago can recur, these are questions that current physics holds open without pretending to answer. The honest position is that we don't know what happens after the last black hole evaporates. We don't know if after is even a meaningful word for that context, if time continues to pass in any physically significant sense when there is nothing left to change. What we do know is the sequence that gets there: the stars burning out, the remnants cooling, the black holes outlasting everything, the last flash of Hawking radiation from the last evaporating black hole in a universe so old that every other process has long since ended, the script that began with the sun's core, with hydrogen fusing quietly in a plasma 15 million degrees hot, with a photon taking 100,000 years to reach the surface. That same physics, followed outward to its endpoint, arrives here, at this cold, dark, patient conclusion. Not an explosion, not a collapse, just the last light going out very slowly, over a time so long that the universe that made the stars is unrecognizable by the time it ends. And yet, right now, tonight, on a planet still warm from a star still burning, none of that has happened, not one step of it. The stelliferous era is ongoing, the stars are there, the sun is there, and the light it made 100,000 years ago is still arriving. That's where this ends. Not in the dark. Here. Right now the sun is on the other side of the planet. It's there. Below the horizon, below the dark, still fusing hydrogen at the rate of 600 million tons per second, still maintaining the equilibrium it has maintained for 4.6 billion years, still sending light outward in every direction, including this one. The light takes 8 minutes to arrive. Some of it is arriving right now at the other side of the Earth, making afternoon somewhere, making shadows lean eastward across a street you'll never walk down, warming the surface of an ocean you've never seen. Here it's dark. The sun is present and invisible simultaneously, which is a condition the sun doesn't notice and we barely register. We call it night and we sleep through it, and tomorrow the light comes back and we don't think of it as the same light that was here yesterday. Though it is. The same source, the same process, the same fusion reaction that has been running without interruption since before this planet existed. I've been sitting with that for a long time tonight. There's a particular quality to a room late at night. The specific temperature of it, slightly cooler than it was in the evening, the heating having cycled down, the walls having given back the warmth they absorbed during the day, and outside, if you live somewhere with trees, the sound of wind moving through them, which is a sound that doesn't change much across centuries, that people have heard in the same register from the beginning of whatever we mean by people. That sound is there tonight. The room is that temperature. and the sun is below the horizon doing what it always does. None of what we talked about has happened yet. That sounds like an obvious thing to say. Of course it hasn't. The sun has 5 billion years of hydrogen burning remaining. The red giant phase is 5 billion years after that. The white dwarf cooling is trillions of years beyond that. And the last black hole evaporating is 10 to the power of 100 years away, a number that shares almost no conceptual territory with tonight. Of course none of it has happened. What else would be true? But I mean something slightly more specific than that. I mean that right now, at this moment, in this particular configuration of the universe, the stelliferous era is ongoing. The stars are burning. Not most of them, not the last few, not the dim red dwarfs in their final centuries, all of them. The sky above the clouds right now contains stars in the middle of their lives, stars near their beginning, stars near their end. The whole range of stellar existence happening simultaneously in a galaxy that is still making new stars from gas clouds that are still dense enough to collapse. The universe is, right now in the phase of its existence, defined by light, by nuclear fire, by the specific physics that makes planets warm and chemistry possible, and somewhere in the long chain of consequences, makes a person lie in a dark room listening to a voice talk about iron cores and event horizons. We are inside the bright part, not forever. We've spent 13 chapters understanding what comes after the bright part, and it comes slowly, patiently, indifferently. It comes. The cooling, the emptying, the long dark patience of the degenerate era, the black hole era, the final evaporation, and whatever formlessness follows. All of that is coming in the same sense that the sun's red giant phase is coming, real, inevitable, written into the physics from the beginning, and also not here yet, not even close to here yet. I think there's something that happens when you spend time with the large timescales, something the mind does almost automatically, almost defensively, where the vastness of the future makes the present feel thin, temporary, slightly unreal, the way a photograph feels slightly unreal compared to the moment it captured. As if knowing the ending in advance diminishes the chapter you're currently inside. I don't think that's right. I've thought about it enough to have a mild opinion about it, which is that the logic runs backward. The fact that the stelliferous era ends doesn't make it less real while it's happening. It makes it specific. Specific in time, specific in condition, specific in the particular set of physical circumstances that allow stars to burn and planets to be warm and carbon to do the strange, improbable chemistry that produces everything we know. This is not always how the universe is. It will not always be how the universe is. Right now it is. The photon that hits your face tomorrow morning, the one that will come through the window at whatever angle the season produces, that will land on a wall or a floor or a closed eyelid, that photon left the sun's core somewhere between 10,000 and 100,000 years ago. It spent that time working outward through the solar interior, scattering and reabsorbing, a slow random walk through plasma so dense that a centimetre was a long way to travel. It reached the surface. It crossed 150 million kilometres of vacuum in 8 minutes. It entered the atmosphere. It arrived. It has been travelling in one form or another since before the last ice age, since before the first writing systems, since before every empire whose name we know, and tomorrow it will come through your window and land somewhere ordinary, on a cup, on a floor, on a hand, and the floor room will be lighter, and you will probably not think about where it came from. That's fine. That's what light is for. Not for thinking about, for seeing by. But tonight, in the dark, with the sun below the horizon, and the cooling happening in increments too small to measure, and the universe somewhere in the long middle of the only era it will ever have that looks like this, it seems worth noticing. Not solemnly, not with the weight of conclusion, just noticing. The iron that won't form in the sun's core, the shockwave that won't propagate, the event horizon that won't exist, the white dwarf that will cool for longer than anything we've discussed has yet existed. All of that is the sun's future, and it is genuinely the sun's future, and it will happen exactly as the physics says it will happen. But the sun right now is burning hydrogen, quietly, steadily, without interruption, on the other side of the planet, making afternoon somewhere, making shadows, warming an ocean, and the universe is full of light. That's where we are. That's what tonight is. Not the ending, the pause, not anywhere near the ending. Just a night inside the bright part, on a warm planet, under a star that has not yet begun to change. It's enough. It's actually quite a lot. If you've made it to the end of this, thank you. Genuinely. This script took a long time and a lot of quiet hours, and it exists entirely because of people who think this kind of space is worth having. Though Sleepy Physicist is self-funded, independently made, and kept alive by listeners who support the work on Patreon. If you'd like to be one of them, the link is in the description. It makes a direct and immediate difference, and it means this continues.